Two engines hang beneath the wings of Boeing's newest flagship. Each one is, individually, the most powerful jet engine ever certified for commercial service. Each one cost General Electric over a decade and billions of dollars to develop, and each one contains technology that simply did not exist when engineers first began sketching the design. Welcome to the GE9X, the engine that made the Boeing 777X possible. Before any discussion of how this machine works, consider the problem it was built to solve. The 777-9 needs to carry more than 400 passengers across nearly 7,000 nautical miles. Two engines must accomplish what older generation jumbo jets required 4 engines to do. The economics demand efficiency. The physics demand power. The contradiction between those two requirements is exactly what GE had to engineer their way out of. Here's the scale dimension that most people fail to grasp until they actually stand next to one. The fan at the front of a GE9X measures 134 inches across, roughly 3.4 meters. That is already the largest fan diameter ever built for any commercial engine. But once you add the nacelle housing, the complete engine assembly reaches 174 inches across. That number deserves a comparison. A Boeing 737 fuselage is narrower than that. One GE9X engine, measured at its widest point, exceeds the width of an entire narrow-body airliner. The 777X carries 2 of these. The mental picture should be unsettling. When Boeing went looking for a power plant capable of moving the 777X, no other manufacturer stepped forward. Rolls-Royce and Pratt & Whitney both passed. The engineering challenges were too extreme, the development costs too punishing, the technical risk too severe. GE became the sole engine supplier by default. The 777X flies with GE9X engines, or it does not fly at all. Now examine what is actually inside this monster. Begin with the most visible parts, the fan blades. There are exactly 16 of them, fewer than the 22 blades the previous generation GE90 used. That decision was deliberate. Fewer blades means each individual blade can grow larger and more aerodynamically refined. The trade-off favors efficiency dramatically. The blades themselves are not metal in any conventional sense. They are sculpted from carbon fiber composite with a titanium strip armoring the leading edge. That titanium protects against the constant assault of bird strikes, hailstones, sand, ice, and air moving at speeds where impact becomes ballistic. The shape of each blade looks almost biological, 3-dimensional curves that resemble something from an ocean creature rather than industrial manufacturing. That organic geometry emerged from extraordinary computational fluid dynamics work, with engineers fine-tuning each surface contour to extract every possible percentage point of efficiency. Why composites instead of metal? 2 reasons: weight savings and durability. A lighter blade reduces stress on the disc holding it, which reduces the mass of the entire engine, which compounds into fuel savings stretching across the aircraft's entire operational life. And the manufacturing process behind these blades is remarkable in itself. Resin-soaked carbon fiber sheets get layered into precision molds by combinations of automated machinery and skilled human hands. Heat and pressure fuse the layers into one continuous structure. Every finished blade endures ultrasonic and X-ray inspection because even invisible flaws could trigger catastrophe at takeoff thrust. Move past the fan and the airflow splits. Most of the air, the vast majority, bypasses the engine core entirely. It flows around the hot section through a dedicated bypass duct and generates the majority of the thrust the engine produces. The GE9X achieves a bypass ratio near 10:1. For every kilogram of air entering the combustion process, roughly 10 kilograms flow around it instead. High bypass ratios sit at the foundation of every modern efficient engine. Move enormous quantities of air at relatively gentle speeds, rather than smaller quantities at violent speeds, and you burn far less fuel for the same thrust output. But the smaller fraction of air entering the core is where the real engineering theater unfolds. An 11-stage high-pressure compressor compresses that air to a pressure ratio of 27:1 within that section alone. Combined with the rest of the compression process, the engine achieves an overall pressure ratio approaching 60:1. That figure is a commercial jet engine record. The consequence of compressing air that hard is heat. Massive heat The air emerging from the compressor reaches temperatures capable of damaging or melting many common metals before it has even encountered actual combustion. The compressor blades must shrink progressively from front to rear as the air densifies. The clearance between every spinning blade and its surrounding casing must hold to fractions of a millimeter because every microscopic gap leaks efficiency. The air then enters something GE calls the TAPS 3 combustor. The acronym stands for Twin Annular Pre-Swirl. Without diving into the fluid dynamics, the system mixes fuel and air in a precisely engineered swirling pattern that produces an exceptionally clean, stable burn. The environmental payoff is significantly reduced nitrogen oxide emissions, one of the most environmentally damaging byproducts traditional jet engines release. This is also where the GE9X enters genuinely futuristic territory. The fuel nozzles inside this combustor are not cast or machined. They are grown through additive manufacturing. GE uses direct metal laser melting, a process where fine metal powder is laid down in microscopic layers and selectively melted by laser into the precise shape required. Layer accumulates upon layer until the finished part emerges from the powder bed. A fuel nozzle that previously required roughly 20 separate components welded and brazed together by hand, is now produced as a single seamless piece. The result weighs less, performs better, and lasts longer than any conventionally manufactured equivalent ever could. The GE9X contains one of the largest deployments of 3D printed components in any production aircraft engine flying today. The hot section that follows pushes material science to its absolute frontier. After leaving the combustor, gases enter the high-pressure turbine at temperatures exceeding 1,300 degrees Celsius during sustained operation. That temperature exceeds the melting point of steel. Conventional metals fail there within seconds. GE solved this by deploying ceramic matrix composites in the combustor liner and the shrouds wrapping the high-pressure turbine. These are advanced materials built from silicon carbide fibers held in a ceramic matrix. They weigh approximately 1/3 what equivalent nickel superalloy components weigh. They tolerate temperatures that destroy traditional metals. The technology essentially uses an engineered version of the same ceramic family found in dinnerware, reinforced at the molecular level to survive inside the hottest region of a working jet engine. Run an engine hotter and you run it more efficiently. Survive that heat without melting and you achieve the previously impossible. The numbers that emerge from all this engineering sit at the edge of comprehension. The certified takeoff thrust rating for the GE9X reaches approximately 110,000 pounds of force per engine. That figure alone would crown it among the most powerful engines ever built. But GE pushed harder during testing. The engine produced over 134,000 pounds of thrust during evaluation, shattering the previous world record for jet engine thrust output. Guinness World Records officially recognized the achievement. Assembly happens at GE Aviation's facility in Durham, North Carolina. The components themselves arrive from a global network. Safran Aircraft Engines in France builds the low-pressure turbine through partnership. Other elements ship in from Japan, Germany, Italy, and various GE locations across North America. Coordinating thousands of precision components manufactured to micron-level tolerances is its own engineering accomplishment. The actual assembly happens largely by human hands rather than robotic systems. Skilled technicians work through each step with every torque setting, every measurement, every clearance recorded and verified. A single engine takes weeks to complete. Then comes one of the most exhaustive certification campaigns in modern aviation history. Bird ingestion tests with actual frozen birds launched into running engines. Ice and hailstone ingestion tests. Crosswind certification, simulated high-altitude evaluation. Extreme cold testing, replicating Arctic conditions. Extreme heat testing, replicating Persian Gulf summer operations. Flight testing followed, performed on GE's specialized Boeing 747 testbed aircraft. The 747 carries one experimental engine mounted on an inner wing pylon for in-flight evaluation. Imagine watching out a 747 window and seeing a single engine nearly matching the 747's own engines in apparent size hanging from the wing. The GE9X first ran on a test stand in 2016. Its first flight aboard the 777X test aircraft occurred on January 25th, 2020, FAA certification followed in September 2020. With the 777X program now targeting service entry in early 2027, the engines that took 14 years to develop are about to begin their actual commercial career, carrying paying passengers across oceans. The efficiency improvement compared to the legendary GE9T it replaces reaches approximately 10%. That figure sounds modest in isolation, but transforms across operational scale. Tons of fuel saved on every long-haul flight, billions of dollars in fleet operating costs across decades of service, significantly reduced carbon emissions per passenger across the aircraft's entire life. And one final detail that surprises most people. Despite being the largest and most powerful commercial jet engine ever certified, the GE9X actually operates quieter than the GE9T. It succeeds. Fewer fan blades, refined blade geometry, larger bypass ratio, and overall architectural improvements combine to push less acoustic energy toward the ground below. That is the engine that will lift the 777X into commercial service. Not just larger and stronger than what came before, fundamentally different, built with materials and methods that genuinely did not exist a generation ago.